Hi, welcome to this lecture on linked lists. So generally, lists have got a number of operations that can occur to them. Firstly, you can access an object that is in a list, right? So if this is a list, you can just say, you know what, I want to see the yellow object. So there's a way you have to do that. Then you can also delete or erase an object from a list. You can also insert a new object into the list, or you can replace an object into a list. So lists can be ordered or unordered lists, right? But lists have got also their own limitations. Usually when it comes to IT, we implement lists using arrays. Now the problem with arrays is that they come with you have to define the maximum number of items that it can take. So let's say it's a class of students, and you say, you know what, my list is supposed to take all the names of the students in the class. Now if you use an array, if today you have 30 students, then you create an array that takes 30 elements. But if your students then increase to 35, now you cannot expand your array because it's limited to 30 students. So that creates a problem when it comes to dealing with information where you do not know how many number of elements you're going to be dealing with. You have no idea of the maximum number of elements you're going to work with, and as a result it can lead to broken programs. So fortunately we have a data structure that you can use called a linked list. So a linked list helps us to overcome this limitation of array-based list implementations. So what is a linked list? So generally a linked list is a dynamic data structure. So by dynamic, it means it resides in memory, right? So it's usually a runtime dynamic, a runtime data structure. So items are added or deleted from that list at will without any issues. So you'll find that when you're dealing now with a linked list, you as the programmer do not need to worry about how many items the linked list can take, because the linked list can take as many elements as the memory of that system can hold. So you'll find that in many programs, as has been said about the array, one of the greatest challenges that a programmer faces is how to deal with an increase in the capacity of a program in the event that the number of elements increases. But with linked lists now, you can actually hold as many elements as you can. The only thing that will limit you is the amount of memory that is in your machine. So linked lists are dynamic data structures. You can add or remove elements from them at any time or at your own will, and they can grow right up to the maximum size of the memory available on your machine. So how do linked lists work? So in a linked list, each item is allocated space as it is added to the list. So let's say this is the first node. Let's look at this node. On this node here, when it is added to the list, it occupies a certain space, and then a link is kept with each item to the next item list. So now with arrays, you see that you declare, let's say, an array that takes 10 elements. When you declare an array that takes 10 elements, those 10 elements reserve space for themselves within memory. So they automatically take up the memory they require, and then they release the rest. But with linked lists now, since you are not going to be storing memory and it's a dynamic thing, the only way you can actually reference the order or the nature of that list is by actually finding a way of tying it to all the other elements. And you tie it using a pointer. Okay, so this next item, so this is the item that we are storing, which is blue. And then this next thing is like a placeholder or a pointer that points you or connects you to the next element, so that no matter where it's the items are stored, there's always a connection between the various elements, hence allowing you to use as much storage as you can. So each node of the list has two elements. It has got an item, which is the value. Let's say this node is storing the value 5, and then it has a pointer to the next, and this pointer named next is pointed to the next item, and this item could be another value, maybe 20. And then this value also has its own pointer. So this is how to the next node. So this is how you create the connections between the various nodes of a list, and hence creating a linked list. So the last node in the list contains a now pointer to indicate that it is the end or tail of the list. So this is the last node. So on the last node now, you can see that there is no way for it to go. So instead of pointing to another node, it just creates a now pointer. Okay, so this next pointer will be called now, such that when you're now traversing through that list, you can act when you get to the end, then to that pointer which is supposed to point next. When you see it labeled as now, then you know that you have reached the end of your list. So as items are added to the list, the memory is dynamically allocated. So as I was saying, the whole purpose of the pointers is to make sure that as we create these nodes and as they are being stored in memory, there's always a way of connecting them, because there's no guarantee that they're going to be stored next to each other, or we can quickly reference their pointers, but I mean their location. But these pointers now help us to create the connections between our various data in memory. So given that now we can use any part of the memory, it means that you may add to the list as many elements as the memory of that system can take. So let's look at a basic implementation of a linked list. So this is a simple code of how to implement a linked list. So at the top there you can see there's a linked list containing 5 elements. The first list node is containing the number 6, and the first node is called the head of the list. So the first node is always the head, and the last node is the tail. So the first node will point to the next node, which will also point to its next node, to the next node, and which will point to the last node, which is 1. And then the last node will have a now pointer, which points to nothing and indicates the end of the list. So the code here is showing that if we create a node class, which is going to create the node or the node object that's going to contain our numbers, within that constructor there, you see that the data that is created or that comes with that node becomes the data for that node. Okay, so in this case, if we declare node A is equal to new node 6, we have created a new node called 6. And then we do the same for node B. We have created a new node B, node C, with these values 3, 4, 2, and 1 respectively. But these nodes are not yet connected. They are independent of each other. So that means all we have done is create these nodes, but we have not yet created the arrows that are connecting them. So how do we create it? That's where that node next variable comes into play. So node next is basically an object that's pointing to the next object. So we are saying node A dot next is equal to node B. So now we know that whenever we reference node A dot next, we are going to get node B. If we call node B dot next, that value of node B dot next will be equal to node C, and the same goes for all those. So at the end of the day, when we say node A dot next, node A contains 6, and dot next now contains node B, and node B contains 3. So we now know that when we are on node A, which is 6, we now point to node B, which contains 3, using that node A dot next reference. So that's a simple and manual way of coming up with a code that implements a linked list. At times you also want to know the number of elements in a linked list. Like we said, a linked list can contain as many elements as the memory of that system can contain. So you'll find that the node is still the same as before, but here now what we'll do is we'll start counting from 1, because a linked list obviously starts as at least 1 element, and the current node is the one that we'll reference as the head of our list. So when we now do while current dot next is not equal to now. So remember we said when you have node dot next, you are referencing to the next object or the next object of that node. So you'll find that here node current is not different from saying node A. Okay, so it's just referencing. So node current or current dot next, if it's not equal to now, then current we move it to the next node, current dot next, then count plus equal to 1. So we increment the value of count. So we continue doing that until we get to the pointer where current dot next is now equal to now, which means we've reached the end of our list, and therefore we stop traversing it, and we take the value of count as the number of elements within that linked list. Now that is called a singly linked list, because it's a singly linked list in the sense that it's only has one direction in which things go. So you can only traverse this list from the head until you get to the tail. There is no way for you to really come back. But with a doubly linked list now, each node has got two connections on it. It has got a connection to the previous node as well as to the next node. So this permits for scanning or searching of the list in any direction that you choose. So you can go backwards in a simple list, but in a simple list, the single list, you will need to go back to the start and then start scanning again going forwards. So that is not really efficient. But the double linked list allows you to search from anywhere. So you find that the main modification of that node object that we are making here is that we have added a node previous link here. So node next links you, works as the pointer to the next node, while node previous works as the pointer for the previous node. So what are the advantages of linked lists? As has been said before, linked lists have got no size limitation. That's the advantage they have over things like arrays. So there's no need for you to be worried about how many elements you're going to use to have. Even if you have 10,000, as long as your memory can hold 10,000 elements, your linked list is going to hold 10,000 elements. Linked lists also are not pre-declared, so you don't have to pre-declare the maximum number of items it can take. It is dynamic and it will grow as the program requires. It also makes insertion and deletion of elements very easy by using our node next and node previous pointers. We can easily get something, or we can actually add our various elements into it. The only challenge it has now is that it requires sequential access. Because for you to access a certain node, you have to go through the pointers of other nodes so that you know where to get it and and then do whatever you want to do with it. So you have to first traverse through the list trying to find the object that's linking to it, and then when you find it, you then do your operations, and then you can leave it alone. So it requires it's a sequential approach to doing stuff. Then also it can take up a lot of space, unnecessary space due to pointers. So you can store, so whenever you're storing a one value, basically instead of using one storage block, you're now using two storage references, where one is storing the actual value and the other is storing the pointer. So that can actually waste your storage space as you use linked lists. So what are the uses of linked lists? Linked lists can be used in web browsers. For example, when you press the back button after you have visited a page and you traverse back, it could be a linked list that is just being used there to check your history or to go to the previous page that you had visited. Then it can also be used in file system handling to connect the various references or spaces that are being used to store the values of one file. So when a file is being stored in storage, it may not necessarily be stored in a sequential manner or in connected blocks, but they could be in different places. So for the file system to know where to get those storage blocks that contain the information of that file, they'll use a linked list to connect them so that they can easily get those files. And you find that linked lists are also used to come up with stacks and queues, which have lots of applications. So we'll talk of stacks and queues, and you see how they work and how linked lists can help them. So I hope you have understood what linked lists are about. I hope you have also thought about how you can actually come up with your own implementation of linked lists, because this example here is an example that has been developed by someone else on how to do linked lists. But you can actually come up with your own example of how to do it. But always remember, as you develop your algorithm, remember the issues to do with time and space complexity to come up with the most efficient algorithm. So thank you for listening.